My name is Dr. Turner. This is University Physics 2, Section P01, and today we're going to be introducing the Biot Savart law. Biot Savart law states that your magnetic field is equal to your mu naught value times your current, all divided by 4 pi, times the integral of dl cross your unit vector r all over r squared. So today we're going to be giving an example on how this can be manipulated to fit your specific problem.
How do you spell Biot Savart?
All right, it's B-I-O-T hyphen S-A-V-A-R-T. And it's pronounced Biot Savart. So typically students get very intimidated by the vector dl across your vector unit r. However, we know doing cross multiplication that if you have a vector A cross product of vector B, you're going to be left with the magnitude of A times the magnitude of B times sine of the theta, the angle that's in between your A and B. Now, if we take the magnitude of dl, we're still left with dl. However, the magnitude for our B value, our r hat, we know that r hat is a unit vector, and so the magnitude of any unit vector is 1. So if your B cancels out to 1, you don't really need to write it. Then you're left with A sine theta. Now typically, in most of these problems, you're going to have a circle with a point at the center. And so your dl is going to be around the circle. And so at any given point, the angle between your point, which is the direction of your unit r, it'll be perpendicular to your dl. So which means that your theta is going to be equal to 90. And so if your theta is equal to 90, your sine of theta goes to 1. So that gets deleted as well. So given that your theta is 90, we would just be left with the integral of dl, and we can pull the r squared out.
When you take the integral of dl, that's just L. But if it's a circle, isn't the length of the circle always the same?
Yes, depending on what it is. If you have a circle, your length is going to be the circumference of that circle. And we know that our circumference is equal to 2 pi r. So when we integrate this, our boundaries are from 0 to L. And when we integrate, it's just L. So we are going to have this all multiplied times your LB value, which was up there, minus your LA value. We had an LA value of 0 because you start at one point on the length, and that's always going to be your 0 point. So the LA goes away, and you can just write your L as a regular L because it's going to be the length of your wire. And this equation is true for a circle. So we've calculated the magnetic field for a circle. Now we're going to calculate one for a line. We're going to start with the same equation. B equals mu naught times your I over 4 pi, all times the integral of dl cross r hat over r squared. Now we went over on how cross multiplication works. So our r hat is still going to go to 1. However, now our point may not necessarily be at 90 degrees all the time. We could have a point here, point here, point here, point here. And we're going to have to find the theta in between that. So we're going to have to dock on that sine theta on the end. And the vector is going to go away because it's our magnitude now. Same thing, we can still pull out our sine theta over r squared. And when we integrate dl, we're going to get the same thing, our LB minus our LA. Our LA is the same as in the other problem because we have to start at one point and we're going to call that 0. So our LA value is 0. And LB is just going to be the total length of the line, so we can just denote that as regular L. So now we have the magnetic field for both a circle and a line given the Biot Savart statement. So now we're going to look at an example where we have a straight line, a quarter a circle, and another straight line with current running through it in this direction. We're going to break this up into 3 different line segments, segment 1, segment 2, and segment 3. We have a point at the center of this semicircle with a distance r and a direction of r hat, and it forms a 90-degree angle with lines 1 and 2. So, given what we know now, our DL is going to be in the same direction as our current. So our DL is going this way, and our r hat direction from our current to our point is running together with it.
Wait, I have a quick question. Okay, wait, isn't the DL the length? Like, that's just the length of the line. So why is
Yes.
it running in the same direction as the current? Like, isn't the length just the length? Like, why is there a direction to the length? Is what my question. Like,
That is one of the rules. That's just how you count it to be able to tell the theta.
but if it's DL sine theta, I thought we got rid of the direction because it's the magnitude. So it's just like the number.
Yes, but you have to know so that you can count what degree it is. That tells you. So if they're running together, you know that the theta is 0. If this were going this way and your point were up there, it would be going the other way, and then you would have a degree of 180. So that's how you can differentiate whether it's 0
Okay.
or 180.
Okay, so like the direction of
Yes.
the current.
You just always count it in the direction of your current.
Okay.
Okay. So since they're both going the same way, the theta would be 0, which would make our entire magnetic field for part 1 0. So that's negligible. Now we look at part 2. The DL is going this way, the same direction as the current, and our r hat direction towards the point is going the opposite. So like you asked just a minute ago, this one would be 180 because they're going in opposite directions. The sine of 180 degrees is still 0, which means that this magnetic field is negligible. So we know that our B total is equal to our B3. We've already gotten the equation for a circle. Now we just need to solve for a value for our L. We know that the circumference of our circle all the way around would be 2 pi r. However, we only have a quarter of a circle right here because we know this is 90 degrees. And so we would simply divide by 4. Those would cancel out, and you'd be left with 1 over 2. So our L value for this quarter of a circle is going to be equal to pi r over 2. We come back here, plug in this chunk for this equation. And then we can just cancel out and simplify.
I have a question.
Yes.
So what if, okay, so like for this one, you knew that it was like a fourth of a circle, but what if you didn't know like if it was like an eighth or like a half? Like it was just some random like thing, like some random little sliver. Like how would you know what it was if it wasn't? You know what I mean?
Okay. So, if we were given an example with lines such as this, and we had just any given theta right here, you would still have the total circumference of your circle, which is equal to 2 pi r. However, you're going to set up a ratio. So your L, you're going to put that over your theta is. And then you'll be able to solve for L. If you're given your theta, all right, and then given L, you would just plug it in this equation the same. So now we're going to go and simplify this one, since our magnetic field at 3 is going to be equal to our total magnetic field. So the square cancels, the r cancels, pi cancels, and then we're left with B equals mu naught times your current. You can multiply your 2 and 4 out, and then it's over 8r. And that would be the value of the total magnetic field in this situation right here. Alright, so who's gonna delete this? I can't be expected to erase this board.